So we get to rely on our formula sheet a little bit, as well as build some experience from our previous work. In lesson 2, we had looked at I equals the principal 1 plus the interest rate to the n, and we have a way of dealing with I and n to talk about growing things. The number 1 that is there is to include the growth factor. I'm always including the growth factor. It's 1 plus percentage of increase. You can imagine that decay can also happen, and that sometimes happens with money. That's always a sad thing. Um, it happens in it happens with exponential decay as it relates to radiation, which we'll talk about today, and it happens to light illumination, which also decreases. And one way of dealing with the 1 plus is to take a look at how your formula sheet describes the topics we're talking about. Our formula sheet describes the topics we're talking about as the growth and decay formula. Y equals AB, it has a T and a P. We've got to get used to what that T and P means, but in this lesson, we're going to look at the B being communicated as a percentage, as well as a half time or a doubling time. So get used to trying to put this formula together. Exponential function, we're going to get growth when b is greater than 1, and we're going to get decay or decreasing in the value of y when b is between 0 and 1. Population growth is a common mathematical study. It's happening in calculus at university right now. They had a really nice population question. In 2012, the university population of a country was 160,000 and increasing at an annual rate of 4.5%. What if we wrote that as an exponential statement? As an exponential statement, you might view it as 1 plus the population increase. And we can write that in an equation format and then try to solve it. So the population P is going to be the amount times 1.045 to the power of n. Determine the population in 2015. Well, how many years do we get for growth? So I get 3 years for growth. So I'm going to go 1.045 to the exponent 3, and then multiply that by my original population of university students. And now, because we're talking about people, we actually should round to the nearest whole number of persons, 182,587 people. Now, if the population were to increase at that same rate, which may or may not occur, determine the number of years for the population to double. Well, doubling is an interesting mathematical relationship. You can simply take 160,000 and double it, which takes me to 320,000. This is actually a very common calculation, which is why we actually have a doubling equation for things that actually double. Divide by 160,000, 320,000 divided by 160,000 is 2. 2 would be equal to 1.045 to the n. From my work previously, I really preferred to take the log of both sides of the equation to begin with. So physically that looks like this: log base 10 of 2 equals log base 10 of 1.045 to the n. Now I'm going to apply that log rule that allows the n to migrate to the front. So n times log base 10 of 1.045 is going to be equal to log base 10 of 2. See if you can solve for n. And I've just had to make my page a little bit longer. So n would be log base 10 of 2 divided by log base 10 of 1.045. Now, to the nearest whole number of years, that would be 16 years. The actual answer was 15.747, but we want the time in years. So let's turn the page over. So this is the first time I'm looking at decay. So instead of growing, I'm actually decreasing. So when I'm looking at decreasing, I'm looking at my growth going down by 5%. Change your 5% into a decimal. So my base is going to be 0.95. And now I want to try to write that equation in exponential form. We're looking to predict the number of fish. So the number of fish at any time t is the original number times my decreasing base, 0.95, to the power or to the exponent of t. So if I had 2,500 fish in 2012, how many in 2017? Well, my t is 5. I have 5 years to lose fish. So that's going to be 2,500 times 0.02 times 0.095. Sorry, 0.95 to the 5. So like I can have doubling time, I can also have halving time. Have 2,500 fish. How long will it take to get to half that number? So 2,500 chopped in half. It takes me down to 1,250. Starting from 2,500. The base is still the same, but I'm looking for that n value or that t value. See if you can find it. My unknown is in the exponent position. I've taken the log of both sides of the equation, moved the exponent to the front, and now I can go log of 0.5, close the brackets, divide by log of 0.95, and find the number of years. It's going to take me 13 and a half years, just over 13 and a half years to reduce the number. I feel pretty good about calling t 13.5, so that's what I'm going to do. In physics, we talk about light sources and their intensity. Some of the students in physics 30 have already seen an interesting video on this type of a law. But the intensity of a light source is reduced to I after passing through fog, according to a formula that's base E. At what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value? So I'm going to set the original value to be 1, and the amount after time t to be equal to 1/4. So 1/4 is equal to 1 times e raised to the exponent 0.12d with a minus sign. So 1/4 divided by 1 is still 1/4. And now because I have base e, I actually get to use that other log function. I'm going to take the natural log of both sides of my equation. So I'm going to apply ln to both sides, which allows me to write this statement as ln of 1/4, or 0.25, is equal to negative 0.12d ln of e. Try solving for d. What's the ln of e? So maybe you remembered, or maybe you had that memorized for our last test, but the ln of e, or the natural log of e, is 1. So I can solve for d by recognizing that ln e becomes 1, and then go ln of 1/4. So that's ln of 0.25, divide by negative 0.12. And I'm going to get a d value to the nearest hundredth of a meter. That's 11.55 meters. Now we're going to talk about expressions where material either doubles or halves. And again, this expression is not on your formula sheet. I would encourage it to be something that you memorize. And both formulas are actually very similar. You can use any letters, A naught, or N or N naught. A stands for original. A naught stands for original amount. So A naught is original amount. And that can be in a variety of units. Hopefully we'll see that. A is the amount after time has passed. Amount after a period of time. And I'm either going to have a base, B, that is either a half for half-life or 2 for doubling. So a half if it talks about half-lives, and 2 if we're talking about doubling. Now, it's possible that there's bacteria that triple or quadruple. So then instead of a 2, there's going to be a 3 or a 4. The expression on your formula sheet does not include a fraction. Take a look at the fraction. The fraction is T over H. T for time passed. H for half-life. And these must be in the same units, both in seconds or minutes or hours or days or years. To make that consistent, both in seconds, minutes, hours, days, or even years. The other formula instead of an H has a D for doubling time. So if you go down a little bit, that same formula is presented, but here I have a D, which is doubling time. But we're going to use the same general idea, an A naught, a 2 or a half, and then the relationship between T and H or T and D. Our knowledge of logs is going to be invaluable. So we're going to do these two examples. I'm going to set up the equation and then see how they're solved. Already I've made some decisions about half-life and doubling time so that I've decided on my bases, and now I've got to figure out what number goes where. So I really like the setup in both of them. I've got things that I can count and exponents that I'm looking to solve for. I use percentages in class example 5. The percentages actually will cancel, which is pretty powerful. I'm looking for the numerator in the second one and the denominator in the first one. My steps are going to be identical. Take the right-hand side and move a portion of it to the left-hand side, and then use logs. So I've left my division until later. I actually went log bracket 8012 divide by 387, close the bracket, divide by log 2, close the bracket, recorded by answer, and that's equal to 24 over D. And then I can solve D for D to the nearest tenth of an hour by going 24 divide by 4.3717, etc. So 5.5 hours. And in a like fashion, I'm going to avoid taking logs till the end for the next one. So the log of 2 over 100 divide by the log of half. So that was log 2 divided by 100 divided by log of a half, which was 5.8643 and some change, being equal to T over 8.1. And then I solve for T by multiplying by 8.1. So I hope these two lessons put logs in a new light. We have a little bit of entertainment. We may have watched that before or afterwards. But welcome to a short week. Thank you.